want to go ahead?
Okay, welcome to this IQTI seminar. We have now increased our outreach to a considerable degree and invited many people both within and outside our institute, and we have a fairly large audience today. Today's speaker is Aram Harrow from MIT. He is an associate professor over there. His area of work is quantum information science and quantum computing, and he is also quite active in organizing and steering various conferences and journals in this particular field. So to give a brief background, he did his undergraduate and graduate studies at MIT itself. His thesis was under Isaac Chuang, and one of the algorithms which came out at that time has become well known by Harrow, Hasidim, and Lloyd, typically referred to as HHL. It's an algorithm to solve a linear system of equations, and they clarified under what conditions it can give a large speed up on a quantum computer. After his studies, he spent 5 years at Bristol as a lecturer and then at University of Washington before coming back to MIT, and he has been there ever since. And he has had actually a large number of students also in this short period who are doing good work. And today's talk is actually on hybrid quantum classical algorithms. These are important in this initial stage of quantum technology development because devices are imperfect, and we have to make best use of what is available classically and combine them with whatever quantum ingredient we can put them in connection with. So we are over to you, Aram.
Great. Well, thank you very much, Apurva, for the nice introduction and for inviting me to speak. Someday I hope to visit in person, but for now it's good that technology makes this easy. I know we're gonna have some question period at the end, but I'm also happy to take questions in the middle of the talk, I should say. And I don't know the Teams platform, so I might not be aware of chat messages, but you can just interrupt me if there are pressing questions.
So just to make a seminar announcement,
yes.
If you have a question, you can raise your hand, and then I will interrupt Aram at a appropriate time, and then you can unmute yourself and you can ask the question. Okay, so thank you.
Great. So I'm going to talk about how quantum and classical computers can work together to solve hard problems in optimization, in inference, things that come up a lot in machine learning, areas where we hope that there'll be a useful quantum speedup, but we have not seen the same level of success that we have for things like quantum simulation or breaking codes. And to give a little bit of context for, what's going to come, the way I've been thinking about algorithms is when we talk about quantum algorithms, there's a quantum algorithm zoo, right? There's a dizzying number of different quantum algorithms. But they're not all, when someone says quantum algorithm, they can mean very different things by it. On a classical computer, you might have, I should ask, I'm sorry, do people see my mouse moving around? My mouse cursor?
Not yet.
No.
Maybe you can use the laser pointer option in that mouse.
Yeah, I see. Laser pointer, good, very good. Now you see it, right?
Yes.
Yes.
So the standard model is what you would expect for a classical algorithm. The input is a bit string, and the output could be a single bit, could be a string. Sort of think of this sort of the conventional model where the input is available on a hard drive or RAM or some kind of standard storage medium. And things like factoring fall into this category. Also, if you want to get a speedup for something like 3-sat, where we don't know of an exponential speedup, that's still something where you have a succinct input in the standard model. And those algorithms are nice when we can get them, but it's been very productive to think of a much wider range of algorithms, some of them more removed from practice. So one of them is an oracle algorithm, and you could say there, or an algorithm with a subroutine, but we tend to call that subroutine an oracle. Instead of your bit string being given to you explicitly, you have implicit access to it via an oracle. So your bit string is still an n-bit string, but you're not given that n-bit string on, say, a hard drive. You're given a function that you can compute, and the truth table of that function is your bit string. So this is a different model. It's a very useful one. This corresponds to Grover's algorithm, as well as other polynomial speedups like the NAND tree and collisions, as well as some exponential speedups like the hidden subgroup problem and the welded tree problem. These are all speedups within the oracle model. And one thing that's appealing about it is that you can prove things about it. If you assume black box access to the oracle, that lets you get a provable speedup. It's also nice because you can compare with classical algorithms. You can say, how did a quantum algorithm with an oracle compare with a classical algorithm with an oracle? Then people found it was useful to think about quantum algorithms with purely quantum data models. So instead of a standard model, you can have quantum data as input, or you can generalize oracles to a quantum oracle. So quantum data could be encoded as the amplitudes of an input state. And that's what happens with the quantum Fourier transform. It's incomparable to the normal Fourier transform because the normal Fourier transform acts on data on a hard drive or data in RAM. The quantum Fourier transform acts on the amplitudes of a quantum state. And there are many other algorithms that are in this category. And for a quantum oracle, instead of being given access to a black box function, you're given access to a black box unitary. And again, there are many useful things we can do with this, like phase estimation is one early example. And in fact, Shor's algorithm uses kind of one from each category, right? It ends with factoring, but along the way, it solved the hidden subgroup problem, it used the quantum Fourier transform, and it did phase estimation. So all of these other models are useful intermediate steps toward building towards something in the standard model description, which is really ultimately what we want. So that's kind of my framework for thinking about quantum algorithms these days. And with that framework in mind, it's always bothered me that we don't have a lot of practical uses of Grover's algorithm. So this is one of the earliest, and even though it's only a square root speedup, I think one of the most mind-blowing speedups of quantum computing because there's just so little structure there. So the Grover's search algorithm is the following problem: given the ability to compute, a function f of I that maps input I to output x sub I. In other words, f encodes the truth table of f is x1 through xn. You want to find a marked element, an I star, that f of I star evaluates to 1. Classically, of course, you need order n time. Grover found you could do this with time scaling like square root of n on a quantum computer. Since then, people have extended this to many unstructured or semi-structured search or optimization problems. And one thing, so this is I think intellectually shocking that there's so little information there, and yet you can get a quantum speedup. But when you try to put it into practice, it's a little bit tricky. The original title was a quantum speedup for database search, and I think that was the archive title that got changed when it got published in PRL. And a lot of people have been confused over the years that this might actually be about databases, but it's for searching oracles, right? The input model is the oracle model. And if you look at here's a database, right? A data center that a company like Facebook or Google might use. And this is not something that you can query in superposition, right? This is not the type of database you would ever search using Grover's algorithm. because you can't, right? You send in your superposition of locations to query, and the classical hardware will just decohere that superposition. Plus, there are better ways of doing it. If you have a ton of hard drives, you probably also have a lot of controllers of those hard drives, maybe not full CPUs, but some kind of processing unit that could do the search in parallel. Or if you didn't, you might as well spend the resources to do it. And one way around this is to propose a quantum RAM, which is something that could be queried in superposition. Or I think quantum ROM is maybe a better name. Think of a CD that you can send a laser beam, and it's going in a superposition of different directions that queries different cells of it. And this is an appealing idea, but it's not easy to build. And I feel like conventional quantum computers are hard enough to build. The experimentalists are working very hard. So as a theorist, I have some obligation to, give proposals of what we can do just with the standard model of quantum computing. So what can we do if you have a bit string in the conventional model on a hard drive, and you want to turn it into an oracle? So this quantum subroutine that you can query that on input I will extract bit x sub I. How can you do it? One approach is this sequence of gates. So you do a bunch of controlled operations. You check if I is equal to 1. You add x sub 1 to this register. That's a unitary operation. It's like a controlled NOT, but instead of being controlled on this thing just being on a single bit, it looks at the entire string. But it's basically like a multiply controlled NOT. And then you step through all n choices. If I is equal to 2, you add x sub 2, and so on. And the quantum computer never needs to make a superposition query to the hard drive. The way you might implement this in practice is your quantum computer is some kind of device like an ion trap or a superconducting chip, and the gates are being sent to it by some pulse generator that's getting instructions from an FPGA, and that FPGA is being fed a sequence of gates like, pi over 3 rotation on this qubit from a laptop, and then that laptop can be connected to the hard drive. And so it reads one record, for I equals 17, it reads x sub 17. It figures out the sequence of quantum gates you need for that, and it sends it to the FPGA, which sends it to the quantum hardware. And so there's no sense in which the quantum computer needs to directly see the hard drive, and it's completely natural for the models of quantum computers that people are building now. But there's a terrible cost here. There's this order n overhead, which is really pretty devastating in terms of trying to get a speed up, right? Because for things like Grover's, remember we went down from n queries to root n queries. If each query takes time n, that's it makes the speed up completely meaningless. So what can you do? As I mentioned, one possibility is a QRAM, so assuming a hardware solution. Another one is what Shor did. So he said, well, if you can find an efficiently computable F, then the truth table of that can be your database. In other words, instead of having an explicit database, you have an implicit database, meaning the truth table of a function. And his idea was that the function is, if you input I, it gives you a to the I mod n. So you come up with a clever function like that, and it turns out that finding the period of this function will tell you about the factors of n. So that's great when you can do that, but of course we can't always guarantee that such functions exist that meet all of our criteria. They're efficiently computable, and answering a question about them will solve some useful problem. So instead, I'm going to propose that we find problems where we can reduce the size of the data set, either with the classical computer alone or in collaboration with the quantum computer. And these will be problems that are generally useful, like clustering, Bayesian inference, and saddle point optimization, problems where, that are quite general purpose, that correspond to things that we want to do where we don't have to make a lot of assumptions about the data, right? So you might have clustering of data points, and you know very little about the quality of the data. So yeah, so let me now talk about that in a little bit more technical detail. Maybe I can pause now if there are any questions.
Professor
Okay, so,
Aram, you can proceed here.
Thanks. So one concrete problem that I want to consider is maximum likelihood estimation. You have a collection of models, Y, and you have a data set, X, and you assume that the data set was that one of the models holds, and that yields some probability distribution for data points, and the data set was drawn IID from that distribution. And so what you want to do is you want to find the most likely model given the data you've observed, so that you're maximizing over little y ranges over space of models, the log likelihood of the data set. So if P of X given Y is the probability of observing data point X given model Y, the log of that, F of XY, is the log likelihood function. And the probability of the entire data set is the product of all these individual ones. So you take the log and it turns into a sum, and you want to maximize that sum. Finally, we can generalize it slightly and say, even in the absence of data, we might prefer some models over others. Maybe we have a prior distribution, maybe we want to favor simpler models. So that can add this additional term R of Y, and sometimes we'll call it maximum a posteriori estimation when you add in this term. So this is a very basic and general problem, and we'd like to know, what can a quantum computer do to speed it up? In particular, Grover's algorithm is one of the most basic quantum algorithms, been around forever. Can we get a Grover speedup, right? Let's at least solve that before we try to, ideally we'd like an exponential speedup, but I'm troubled by just not even knowing if I can Grover it. So let's look at that. So if you look at this expression, max over y, sum over x, the x and y appear almost symmetrically. There's a max over y and then a sum over x, but both of these are things that you can get a Grover type speedup for. But the big difference is in the type of data set. X is a real explicit data set that lives on a hard drive. So I do not have superposition access to it. I don't have an Oracle access without going through this procedure that gives me this terrible overhead. Y is you could call it a synthetic or an implicit data set, something we do have superposition access to. For example, if it's a clustering problem, you might have all the possible weights and centers of clusters. There are tons of them, but you don't have to list them all explicitly on the hard drive. You can, you can just, we kind of have a mathematical description of the set of possible clusters. Or if you, let's say that you have a problem that you're going to solve with gradient descent, like you want to tune the weights of a neural network, but there are many, many local minima. Y could be the set of starting points of gradient descent. So it doesn't have to be that you're just blindly searching over all the parameters. Your procedure could include some process like gradient descent, but you still, even with that, there may be a search over a large number of things, and those again can be should be something that you have a mathematical description of, not something you have to look on a hard drive for. So what does that mean in terms of the Grover speedup? It means in our conventional model of quantum computing, we can get a Grover speedup over the outer loop that searches over Y, but not over the inner loop that iterates over X. So the number of quantum evaluations of F we are going to need is going to scale like the size of X times the square root of the size of Y. So we can speed up the Y part, but not the X part. And if you think we have a better speedup than Grover, like maybe you have a reason to believe that adiabatic would work really well, or you have some other clever optimization algorithm, and you get a better speedup over Y, then leaving the X intact is only more painful, right? This X factor becomes more and more important as we get better speedups in terms of Y. So what can we do about X? How can we reduce the dependence on the data size, given that we don't have superposition access to the data? So the proposal I want to put forward, which is something that's taken from the classical machine learning literature, which in turn took it from computational geometry. The idea is something called a core set, that you can take a large database like this X and approximate it by a smaller one, which is a weighted subset of the original points. And we say that X prime is a core set if for all model is Y. You could make it just the best model, but it turns out to be not that much harder to say all models. The true log likelihood function, so for Y, you sum over all the data points X, is close to the approximate one that you get from summing over X prime. And you have to put these weights on the data points, if nothing else because the number of terms has changed a lot. There are many fewer points in X prime than X if you want to get significant savings. But also because, excuse me, you might be doing some kind of importance sampling. You might not choose every point with the same probability. For example, for clustering, if you have a large, the ideal core set would have a similar number of points from each cluster, maybe even 1 point from each cluster. But some clusters are big and some are small. And so you want the points in the big cluster to have a big weight to reflect the fact that they effectively represent many points in the original data set. So the weights are also a crucial feature of this. So this gives rise to a very simple hybrid algorithm for machine learning. You have a big data set X. It goes to a classical computer that produces a core set X prime. And now the data set is small enough that the quantum computer can analyze it and produce a model Y. And if you pay an overhead of iterating through every point in X prime in the inner loop of your quantum computer, that's okay because we've managed to make X prime much smaller. So in a little bit more concretely, how does this work? There are many ways of making core sets. One is you can produce a very crude approximation of the best model. So for example, for clustering, you could use a heuristic like the k-means algorithm that will provide you a sort of an approximate clustering. And then you can use that to construct what are called important sampling weights. So this will give you a sense of, for each point, is it likely to be in a really big cluster? And then we can put it in with small probability, or a small cluster, in which case we should put it in with higher probability. And that way we ensure that we make it more likely that we'll hit all the clusters. The key thing is here, if you just do uniform sampling, you'll miss all the small clusters. And in some cases that may be okay. In other problems, the small clusters might be precisely the interesting outliers that you're looking for. So you oftentimes, cannot get away with uniform sampling. You need some way of coming up with important sampling weights. Then you use these weights to sample X prime. Then you pass this to the quantum computer. And I've been saying Grover the whole time for both for completeness and because it's an old problem. I want to know what you can do with it. But everything I'm saying would also apply to using quantum walks, the adiabatic algorithm, the quantum quench algorithm, any other optimization algorithm. This would also apply to. Now the cost of the inner loop scales with X prime, and the total cost of the algorithm for Grover, let's say, is going to be the size of X prime times the square root of the size of your search space. And this gives you a provable speedup for problems like clustering. So for clustering, the best known classical algorithms, I should say provable, it's sort of the runtime, if you assume that the best known classical algorithm cannot be improved, right? So we don't know that there's not a better classical algorithm, but the best known classical algorithm produces a core set and then brute forces over clusterings of that core set. And so by replacing this brute force part with a quantum computer, you get the quadratic speedup of that brute force search without having to waste a lot of time iterating over the whole data set. So that is the first proposal I want to give for a hybrid quantum classical algorithm. And I think this is a useful framework for for real problems like clustering. But you might object that it's really more of a classical than a quantum algorithm that I presented, because by the time we've turned on the quantum computer, the data has already been reduced by the classical computer. And in fact, the classical computer or some kind of classical computing devices were the ones that acquired the data in the first place. So it's a little bit like this is the mama bird and this is the baby bird that's in the nest. The mama bird goes out, gets the food, brings it back, chews it up, and regurgitates it to the baby. Can we have a more glorious role for the quantum computer here? And can you expand the range of what you do by using the quantum computer interactively, by saying, analyzing the data you've got and then sending a message back to the classical computer, getting it to explore other parts of the data set? And
Jaideep has a question.
Yeah, hi. So I'm a completely a non-expert in this area, but I had a sort of a quick question on this this conversion from X, or transformation from X dataset X to X prime. So a couple of things. So one is that this is not unique. So that's question one. The question two is that is there a way that you can basically provide an estimation of the accuracy of the eventual final outcome in terms of how well X prime, the transformation from X to X prime is done? I mean, in other words, I can to speed up things, I can go to a very, very small dimension of X prime, but obviously that will not be very accurate representation of X. That's your original data set is X. So these are the couple of questions that I had.
Yeah, good question. So the reason why I glossed over that is because this is the stuff that is done in the classical machine learning literature where I'm not adding to, but these are interesting points. So sorry, I stopped the sharing because I have some hidden slides here on this. Let me unhide these slides and let me reshare it. Yeah, and so in general, this will induce some errors.
Your screen is very small.
Do you see it at all?
Yeah, we see it, but it's very small.
Okay, so let me just reshare it. How's that?
Yep.
It's good.
Good?
Yeah.
Okay. Yeah, I've also done it now. It's doesn't take up the whole screen, so I can now see you on. I can see the videos too. So yeah, very good question. So this process will introduce errors, and there will be a trade-off between the size of the core set and the amount of error. So the bigger the core set, the more you pay, but the lower the error will be. And the high-level point is this cost is going to depend on a few things. So the size of the core set is going to depend on the error that you want, and it's going to depend on the complexity of the model that you're fitting, and yeah, basically those two things. And just to see a little bit how this works, the way importance sampling works is you want it so that the log likelihood, the true log likelihood is approximated by this, what you get from the core set for all, for all models. And you can think of this, you can break this into three parts. You can say, well, first of all, think of the core set as being chosen randomly via sampling. And so the right-hand side is a random variable depending on my random choice of X prime and the corresponding weights. And I want this right-hand side to have the same expectation value as the left-hand side, And that's saying that this should be an unbiased estimator of the left-hand side. That's point number one. Second, I want the variance to not be too large. So for any fixed y, I want this variance here to be reasonable. And that if those are true, then it'll be like for any fixed model, this will be likely to be good. But then third, you have to do some kind of union bound. You know, this has to work simultaneously for all values of y. And so that's kind of the third challenge. And the solutions to these are, the first one is the basic idea of importance sampling, which is if you take x with probability at proportional to s of x, the weight should be inverse in that. So if you boost the probability at some point, you should put down the weight by a corresponding amount. That's how you get it to be unbiased. Then what these weights are will can be related to something called sensitivities, which means how much does the how much of a model score comes from one data point. If one data point is very influential, then we say that that point, you know, that point is then the overall model can be, in principle, quite sensitive to that one point, and S of x should upper bound all of these sensitivities. If you actually look at the definition of sensitivity, it looks quite hard to compute. It's as hard to compute as the original problem. So this is infeasible. But if you just have an upper bound on it, then that's enough for the problem. And then finally, when you want to do this sort of union bound thing where you want this to be simultaneously good for all models, you need some way of talking about the complexity of the space of all the models. And if you're familiar with VC dimension, that's one way of doing it. Or there's a variant called pseudo dimension that basically can quantify how complex your space of models is. Then there's this theorem, there's a nice review paper by these authors, which reviews a lot of work on coresets. And they argue that if you take the size of the coreset to be m, we need m should scale like the pseudo dimension d times the square of the total sensitivity divided by epsilon squared, where epsilon is the error you're willing to incur. Now, when you look at this total sensitivity is a sum of the sensitivities of every single point. So you might worry this might scale with the size of the data set. So in the worst case, you know, there's no free lunch. This doesn't work for every possible model. You can cook up weird functions where there's really no savings to be obtained from coresets. But for a lot of common problems like you know, finding k clusters in d dimensions, you can bound the pseudo dimension scales like the dimension times the number of clusters. The sensitivity goes like the number of clusters, and you get an explicit bound on the size of your coreset, which does not scale with the size of the original data set. It just scales with the complexity of the problem, you know, like this dimension and so on, but not with the size of the original data set. And this size of the coreset is where it's going to dominate the cost of your brute force search over all clusterings. And so, you know, once you found that, then, you know, cutting down that search is what a quantum computer can help with. Does that answer your question?
Yeah, I get a good sense of it. Yeah, thanks.
Sure. And I should say that there are other ways of doing coresets as well. So there's a rich literature on this. This is, I think, one very general and concrete way, but there are many other techniques as well. In fact, I'm going to tell you about some of these techniques that are interactive. So that benefit from using the quantum computer, yeah, and feeding that back to the classical computer. And I want to do this now for a slightly different problem. What I said before was you pick the most likely model. But let's say you care about uncertainty. So you want to output some estimate of, you know, what is the range of uncertainty in the model that I'm estimating? And this can be done, one way to do this with Bayesian inference. And what that means is you have a prior distribution, pi naught. You still have the same data generating process, and you observe a data set X, and then your posterior becomes pi of Y, which is basically take pi naught, multiply it by all the log likelihoods, and then normalize. So you'd like to sample from this posterior distribution that will tell you about which models are highly likely, not exactly the most likely one, but which ones are in the highly likely set. And there's an adaptive coreset procedure for doing this, where the classical computer in the tth step has a coreset of size t. So here the points in the coreset as well as the corresponding weights. And then the quantum computer will sample from the not the true posterior, but the posterior given by this coreset. So you replace the full data set just with this weighted one from the coreset that gives rise to some posterior, and the quantum computer can sample from that. And I should say here that I've been talking a lot about Grover, and one objection to Grover is that it's a quadratic speedup of brute force search. But brute force search is often not the best classical algorithm, not by a long shot. For sampling problems, we can do a lot better. There, if the best classical algorithm, let's say, involves a random walk, let's say you're doing a simulated annealing, this is a problem for which we have a quadratic quantum speedup. So we have a quadratic quantum speedup relative already to what can often be the best classical algorithm. Now, classical algorithms are moving quickly. There are things like Hamiltonian Monte Carlo that we don't have quadratic speedups of, but we do have quadratic speedups of pretty competitive algorithms. So then we've sampled a model from this distribution, and now the classical computer looks at the existing coreset and all of the models that have been sampled so far and chooses the next point of the coreset based on all of that. And so it can look at all the models and figure out a point in the data set that's not well fit by those and include that in the next coreset. And so in that way, it can reach corners of the data that might otherwise have been missed by any non-adaptive procedure. And there's a few procedures for doing this. There's a very concrete one due to Campbell and Broderick. And I'm not going to get into it. I mean, I can if you have questions, but I wasn't planning to because it's again, this is a classical procedure, and I want to emphasize the quantum part, and you could imagine other ways of doing it as well. But instead, I'll talk about a very specific example where I fully specify what the classical and quantum computer do, and how well and what the quality of the speedup is. So the Campbell and Broderick procedure is something where it's basically a heuristic. It's an algorithm where they have a performance bound that's based on parameters that we don't know. It's a little bit like when you have a Markov chain, how quickly does it converge? That depends on the spectral gap, but we don't know what the spectral gap is in general. So often when we run it, we just don't know what kind of performance to expect. So the same thing here. It's a plausible heuristic algorithm, but we don't know what kind of performance to expect. So instead, let me give you a third example, which is where I can tell you exactly what the runtime will be. And this is again for a slightly different problem. It's one called saddle point optimization. What I'm going to do now is instead of, so the data set is still x1 through xn, but I'm going to define capital X to be the convex hull of those points. Here's a little drawing of that. It just means the smallest convex set containing all those points. Oh, I'm sorry, I lost the laser pointer, right? Let me put that back on. And is that right? You don't see my mouse anymore, right?
No.
Okay. So let me put that back on. So X is the sorry. Yeah, that's because I didn't do full screen.
Okay.
Well, okay, let me do this, and then let me reshare it. And now, oh yeah, here we go. Good.
Yes.
And I'll take Y to be the space of probability distributions over M items. So you could think of those basic M items as like M basic models, but I'm going to also consider combinations of them. If you're familiar with the boosting procedure in machine learning, that's what this does. And I'm going to define f of xy to be linear in x and y. So whatever my score is for, the basic one model over one data point, if I take a mixture of models or a mixture of data points, then I just let f be I define it as the linear combination of the underlying values of f. And now the problem that I want to solve is the minimax problem. I want to find the best model over the worst data point. Or equivalently, I could find minimize over data points and then maximize over models f of xy. And this equality is von Neumann's minimax theorem. It holds because of these assumptions that I've made above. And it occurs in many different problems. So the way I've expressed it, it looks a lot like a zero-sum game, right? Where the X player is trying to minimize the score and the Y player is trying to maximize it. Of course, it's important here that X be an actual based, again, an explicit database, and Y be an implicit database, something that we have a mathematical description of. Another example is linear programming. So suppose I want to find a point in the probability simplex of dimension m, and I have n constraints. Each one of these encodes some kind of hyperplane, some kind of, and my points have to lie on one side of that hyperplane. And so I can define the inequality is basically saying that a certain linear function has to be greater than or equal to 0. And if all of these things, if I have a valid point, then all of these linear functions will be greater than or equal to 0. And so the minimum over x will be greater than or equal to 0. If my point is invalid, then there'll be some violated constraint, and this minimum will be less than 0. So asking whether I can find a point y such that this minimum is greater than or equal to 0 is basically asking if I can find a feasible point in this linear program. The family also includes not exactly maximum likely estimation, but it's close to it, because if you replace the sum in maximum likely estimation by the minimum. So if you think of a clustering problem where instead of caring about the average performance of all the points, you care about the worst case one. You just really want to make sure that there's no single point that's badly fit by the model, then that corresponds to this sort of minimax problem. And if you're familiar with SVMs, usually those use an L2 norm, but if you use an L1 norm instead, then that corresponds to directly maps onto this sort of problem as well. Okay, so how can we solve this? I'll describe an algorithm for it in the context of zero-sum games. So I'll describe an algorithm for solving one of these minimax problems by thinking it as a game, because they're all kind of equivalent. And this is a classical algorithm, but which adapts very well to this hybrid quantum strategy, hybrid quantum classical setting. It's due to Grigoriadis and Kachian. And it's called fictitious play. You can imagine, players playing this game and trying to improve their strategies. And I'll illustrate it for rock, paper, scissors. So here's the payoff matrix for that. And so the Y player wants a positive score and the X player wants a negative score, and 0 means a tie. And one thing you can see from this is that just doing the best response will not converge to an equilibrium, right? Because if the X player does rock, then the Y player does paper, and the X player does scissors, and the Y player does rock, and it's just going to cycle forever. It will never converge. But if you add a little bit of noise, then it will converge rapidly. So how does that work? The X player will choose some strategy arbitrarily, let's say rock, and then the Y player will choose a strategy that is not exactly the best response, but is biased towards a better response. So there's going to be some parameter epsilon, and it's going to, the probability of a response y1 it's going to scale like e to the epsilon times the payoff given what the X player did. So the higher payoffs will be more likely to be chosen. The most likely will be, and here's this purple row, is this vector of payoffs induced by the X strategy. So the most likely will be paper, the least likely will be scissors, and let's suppose that the Y player happens to choose paper. Then we go back to the X player, and we say that paper induces these payoffs for the X player, and we do the same thing, except now there's a minus sign because the X player wants to minimize things. So the most likely for the X player is scissors, and the least likely would be rock. And again, it's a random procedure, so it will not always choose the best one. Let's suppose that the X player chooses paper this time. Now there are two rows. So now there's, the X player did rock in the first one and paper in the second one. The Y player responds to the sum of each of these payoffs. And so if epsilon is small, the initial payoff vectors, when they're multiplied by epsilon, are all going to be pretty close to 0. So the players are sort of bouncing around at random. But as you keep on doing things, and if you repeat a row, you put that in with the appropriate multiple, the bad strategies become exponentially less likely, and the players will converge rapidly to a good strategy. And so their theorem is that the error, to get it down to epsilon times the largest entry of the matrix, the number of rounds you need goes like the log of the number of strategies divided by epsilon squared. So the scaling with the size of the problem is very good, and the scaling with epsilon is not so good. And so this is competitive if epsilon is not too small, but you have a very large solution space to look over. And this works very well for this hybrid model of computing because there are, if T is not too big, there are T rounds of alternation. And what happens in each round, the classical computer has to look at every point in the data set and evaluate that against what the quantum computer sent it, the T strategies the quantum computer sent it. The quantum computer needs to grow over its strategies or do whatever search algorithm is best for that. And the number of calculations in the inner loop it needs scales like the number of data points that the classical computer has sent, which again is order T. And so if T is not too big, this is pretty close to the least you ever could have hoped for, right? Because you assume the classical computer has to go through the data set at least once, and the quantum computer is willing to do one round of Grover over its strategy space at least once. And so if T is small, this is pretty close to the best you could hope for. And of course, when you have a problem that fits this sort of hybrid model where one player's data set can be described by an explicit data set on a hard drive, and the other one can be described by implicitly. But this fits the examples I've described. Like you have, you want a model that does well on the worst data point, where you can, there's settings where that might be natural. So yeah, maybe I can pause briefly for any other questions.
Aram, just to point out, there are about 10 minutes left in the the talk.
And should I leave time for questions, or 10 minutes and then we do questions?
Yeah, 10 minutes and then we can do extended session of questions. Yeah.
So I have to mention very briefly some work with my student John Knapp on the other kind of hybrid algorithm that people usually mean when they talk about hybrid algorithms. They mean variational algorithms. And the idea is you have something you want to minimize, some energy, over an ansatz. So you have a starting state psi naught, and you have this parameterized family of states given by these parameters T1 through TP. And this includes combinatorial optimization. So if you know the QA-OA algorithm, that's of this form, and something called the variational quantum eigensolver, where basically instead of trying to minimize a classical combinatorial problem, you're trying to find the ground state of some Hamiltonian. And there's a common picture, which is you have a classical outer loop, which is to search over these T1 through TP, and the inner loop, the quantum computer is estimating the the objective function. And this is very appealing as a near-term algorithm because the you can make p quite small, and then this becomes something that's feasible even with a very simple quantum computer. And it's appealing because if you take p large enough, maybe even exponential, so it's that part is it's not that great of a guarantee, but if p is large enough and you find the right parameters, then this is known to include the exact answer. So even though there's some serious caveats there, at least in principle, this approach, there's no limit on how accurate it can be. So one thing we looked at was, should you be looking at the function value? So f of t is the value, the expectation value of h, or should we be looking at the gradient? And there are many algorithms for each. So you could say a 0th order method looks at the function value, first order looks at the gradient. There's also second order, which looks at second derivatives. And one thing we did is we found, first of all, that you can estimate the gradient with basically by a procedure, which I won't get into details of, which is only slightly more costly than estimating the function value. So the coherence time that's needed, it might take more repetitions, but the coherence time, the amount of time you have to run the quantum computer, is very similar to what it is for 0th order estimation. There are other strategies where if you're willing to use a lot more gates and ancillas, you can get much more accurate estimates of the gradient. Basically, you can estimate all the components of it at once. But if you want to estimate just one component of the gradient, you can do that with a cost similar to estimating the original function value. We also found some performance guarantees, which I think I don't want to talk about. I'll talk about this other result that we have, which is we show that contrary to some intuition that people had given before, that 0th order might be better because you can estimate all the commuting terms of the Hamiltonian at once, versus to estimate the gradient, you only get one component of the gradient. We found for a very, very simple problem, so basically your objective function is just a sum of single qubit terms. So there's a poly z and then a poly x on each qubit, and there's just some kind of unknown shift in what this poly x value is. We found that gradient descent does better than 0th order methods. So 0th order methods scale like n cubed, that's the number of qubits, divided by the precision epsilon squared. And first order methods give you better scaling for both the number of qubits and the accuracy. And one kind of ongoing thing we're looking at now is, could second order be even better? And one theme from the earlier part of my talk on coresets is that we should be making more use of powerful classical computers. And I believe there's more room for this as well for these more conventional variational algorithms. And I think I'll skip this part. Yeah, actually, I'll mention one other thing, which is our analysis, when we talk about first order and 0th order algorithms, this is in the vicinity of a local minimum, but reaching it is the hard part. And one phenomenon that was observed is something called the barren plateau phenomena, where your objective function kind of looks like this, super flat, even though you're far from the minimum. The minimum is down in the ocean here, but you're kind of stuck in this very flat region where the gradients are close to 0, so you don't know where to go. And John Knapp is working on a paper now where he strengthens the earlier results by McLean et al. And shows that really, if you have a random initialization, the gradients vanish quite quickly. And in my other student, Eric Anschwitz, has found that if you look at this barren plateau region, it actually looks it has teeny little bumps in it. So the gradients are small, but there are many, many, many local minima. And we observe this numerically here for the transverse field Ising model. And so these are some difficulties with these approaches, is that you cannot just initialize at random. Like once you're in the vicinity of a local minimum is good, but reaching a local minimum is still really a hard problem that will require more work. Yeah, and maybe the last thing I'll say is I've presented on kind of two papers that look fairly disjoint. One of them is on using the classical computer to access a big data set. The other one, the main use of the classical computer is just to keep track of where you are for gradient descent. And I'll mention that there's actually kind of a relation between them. These variational algorithms that use gradient descent, you can view gradient descent as if your first point is x sub t, you choose xt plus 1 by moving in the direction of the gradient and adding a penalty term which says I don't want to get too far from the previous point. Sometimes that's called proximal gradient descent. But that penalty term doesn't have to be the Euclidean norm. You could also, if your points live in the probability simplex, you could use the relative entropy. This d of y given x is the relative entropy. And if you do that, you get a different update rule called the multiplicative update rule, where your probabilities get multiplied by e to the minus your step size times the gradient. And so if you use this different form of gradient descent, this basically gives rise to the saddle point algorithm. And so you could say that what I've done with the saddle point algorithm is a special case of more general hybrid gradient descent algorithms, but it's done in a very special way that basically lets you not look at most of the data set. If you kind of generically do gradient descent, you'll find yourself having to look at all of the data set. This one, the reason for this sort of mirror descent is it lets you avoid looking at most of the data set. So let me wrap up and just say that quantum computers are hopefully coming, but classical computers are always going to be cheaper. So we're always going to want to find ways for them to work together. And I'll close by mentioning one other example of hybrid computation. So this is something that after Kasparov lost to a computer to Deep Blue in chess, he helped popularize this idea that had been around before, but he helped popularize the idea of a human and a computer playing together. And sometimes this is called centaur chess. And there was this nice window when the top-rated computers had a chess rating that was below that of the top-rated human and computer teams. And unfortunately for humans, we no longer add much value to chess-playing computers, at least not when playing alongside of them. And this also, maybe the situation for classical and quantum hybrid algorithms, it's not always obvious when you can get both of the, when both partners are equally necessary to it. But I think there's a lot of scope for different ways of combining classical and quantum computers. And yeah, I'm excited to keep working on it, and I hope some of you will also come up with different ways of combining these computing platforms. Okay, I'll stop here, and thanks for your attention.
Thanks, Aram. That was great. Thanks for giving such a wonderful talk. Yeah, time for questions. Please go ahead with your questions. Okay, maybe I will start with a question. Okay, maybe Apurva, do you want to ask something? Yeah, please go ahead, Apurva.
Yeah. In the problem of classification of data, you mentioned the concept of a pseudo dimension to simplify the amount of data needed. So are there any straightforward methods to estimate this pseudo dimension of the data? I mean, some of the directions basically can be useless. That's what you mean.
Oh yeah, yeah. So the pseudo dimension is actually the pseudo dimension of the space of models. So for example, for the models we might have would be I'm going to cluster it into k centers in D spatial dimensions, that is and the question is basically how rich is that space of models? So how many how many points, like what's an intuitive way of putting it? It's sort of like saying, I mean, I'll give a very simple example, which is, polynomials of degree d, right? A polynomial of degree d can exactly fit d plus 1 points, right? And not more than that. So d plus 1, so when you say the polynomials of degree d, there's a certain sense in which it's the complexity of this models is on the order of d, because it can exactly fit, any d plus 1 points can be fit by it, and so it's yeah. So that roughly tells you the complexity of the model. So similarly, if you have if you have something like this clustering problem, the number of the cluster centers and the ambient dimension of the space tells you basically how many points can you fit arbitrarily by it, and that will grow. That will basically just depend on the complexity of the model. It will not scale with the number of points in your data set.
No, for example, there is a concept of a rank of a matrix in linear algebra, which basically gives you an idea of how many independent directions there are.
Right.
So there is something similar which one can do with respect to these models as well.
So I think maybe the way of thinking about rank here would be, let's say I have a giant matrix, and then I want to approximate it by a low rank matrix. So then the low rank matrices would be like the set of models, and the underlying, the original giant matrix can be my my data set, which I then want to approximate by one of my models. Right? It doesn't have to exactly fit the model. Like the matrix you're given might not be exactly low rank, but you may want to approximate it by the best fit low rank matrix. So then this would, so that's why the set of low rank matrices is not something that depends on your data. That's just how you're choosing to model things. Right, and then your actual data could be whatever it is. The pseudo dimension will not depend on your actual data. It will just depend on the space of models. The sensitivity might depend on your data, and that's the one where, if you're not careful, that could scale with the size of your data set. But for but for many problems, it turns out not to. But that's not something which is a priori obvious. The sensitivity couldn't grow with the size of your data set. I'll put up this slide again just to remind what these terms are.
Okay, should we move to the next question? Venus, please go ahead and unmute yourself and ask your question.
Yeah, thank you, Professor Aram, for this nice talk. So I have just a simple question. So if I understood it correctly, so if quantum search algorithm can be implemented successfully using a quantum computer, and suppose we can assign the sampling weight successfully for a classical data set, then that problem can be solved using this hybrid approach. So my question is, like, what is the limit of this approach? Like, which problems need not be solved or need not be thought of solving using this hybrid approach?
Good. Right. So there may be problems where data reduction. Yeah. Okay. So a few possibilities. So it may be that data reduction just doesn't work well. You could imagine. Yeah. I don't know of very natural problems where data reduction doesn't work well, but you can certainly have kind of contrived problems where data reduction doesn't work well. For example, if you want to suppose your Bayesian inference problem is, let's say all your points belong to some discrete set, and you want to sample from a point that's not equal to any of the ones you've seen so far. That's one where that just does not work well. There's not a good coreset way of approaching that. The reason for that, I guess in that case you could look at it in terms of, these parameters of total sensitivity and pseudo dimension, that those would be very large. And let me think about I guess another one might be, so another limitation is that, let's say that everything does work out, but you want to the scaling may still not be favorable enough. So it may be that the accuracy you want, like these work well in the regime of fairly low accuracy, but if you want super high accuracy, then maybe this would become less competitive, because you're only like bringing down the error by sampling. So it may be that you just need simply too many samples in order to bring the error way down. And another limitation, of course, is for optimization, we don't really know what kind of beyond Grover speedups we can expect. There are a few examples, like Tongying Li and a few other people have this exciting paper where they get a cubic speedup and escaping saddle points. And Matt Hastings has a few really cool speedups for optimization problems. They're not fully general, but they're fairly general. So there's some scope for for beyond Grover speedup, but we don't really know how well it's going to work. And it could just be that that we find that in many cases a quadratic speedup is just simply not enough. So it could be also that this does work, but that the advantage is not enough to be competitive. So I think, those are some of the main limitations I can think of.
Okay. Thank you very much. Thank you.
Sure.
Okay. Any more questions for Aram? Okay. If not, if I can request everybody to unmute themselves and just like give Aram a round of applause for a wonderful talk, that would be great. So, Aram.
Thanks, everyone.
Oh, great. So Aram will be still here for some more time. So if you want to hang around for a bit, I think Apurva and I'll be here. So everybody else, thank you.